Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at a deep dive into calculus where we're going to reason with definitions and theorems. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. Tonight we're really lucky to be joined by our two panelists, Jan Michener and Dennis Wilson. Jan has been a mathematics teacher for over 35 years, teaching courses all the way from Algebra 1 up through Calculus 3. She received the Presidential Award for Excellence in Science and Math Teaching, is an AP Calculus reader, and has been with the T-Cubed organization since 2003. Her passion is mentoring and training teachers on using technology as a tool to enhance learning. Jan, thanks so much for being with us tonight.
Thanks, Mike. It's great to be here.
And Dennis is in his 23rd year of teaching, all of which have been at Landmark Christian School. He has been teaching calculus since 2001, and he's an active member of the Georgia Association of Advanced Placement Math Teachers. He's currently serving as the president of that organization. He has served as an AP Calculus reader for the past 3 years. So Dennis, we're really glad to have you with us tonight.
Mike, I'm really glad to be here. Very excited. Thank you.
We're expecting a large crowd, so your audio is muted. Feel free at any time to send any questions to Jan or Dennis using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, this session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We hope you don't have any audio issues, but in the event that you do, try selecting Communicate from the top of the WebEx menu and choose Audio Broadcast. At this point, Janet's going to discuss our agenda.
Thanks, Mike. Well, tonight we're going to kind of dive into the mean value theorem. We're going to look at the average rate of change graphically, use technology to reinforce average rate of change. We have a mean value theorem exploration using two runners. We're going to be using two intervals at which the mean value theorem conditions are met and finding those, and graphically find values guaranteed by the mean value theorem.
Thanks so much, Jan. And Dennis is going to discuss our expected outcomes.
Thanks, Mike. So tonight we want to explore average rate of change and mean value theorem, both graphically using technology. We want to discuss how the mathematical practices for AP Calculus, specifically one we'll look at, apply the mean value theorem and the average rate of change. And we're going to discuss the conditions, the hypotheses that need to be met to apply the mean value theorem.
Thanks so much, Dennis. Give me 1 second. I'm going to give you control. All right, Dennis, you have control. Feel free to share your screen.
Thank you. So the first mathematical practice for AP Calculus is reasoning with definitions and theorems. And we're going to look at using that as we explore the mean value theorem. Two points I want to make in these subpoints. First, I want to point out the words hypotheses and conclusion. When I talk about theorems in my class, I also use the words condition and consequence. My students need to understand that there's an if and a then. And so tonight, we want to look at what is the conclusion first to help students understand why the hypotheses would need to be met. And we're going to help students develop conjectures based on explorations we'll be doing with technology. One of the big problems my students have when they enter my pre-calculus class is they're all linear thinkers. And when they come in, to them, every graph is a line. They have a hard time understanding the concept of average rate of change because to them, all rates of change are constant. So to help students develop a sense of changing rate of change, I use a position time graph. We're going to look at that now. And what we have on this is a position time graph for a runner in a race. So what I want you to do is to take 30 seconds and look at this graph and think of two things. First, what information would you want your students to be able to tell you about this race? And then what information would you actually get from a student when they first enter your calculus class about this race? So some of the things that I would want my students to see is, first of all, that the race had a distance of 30 units. Maybe it's a 30-meter race, and that race was completed in 6 seconds. The next thing I want people to see is that the runner starts very quickly. We can see that in the first second, he covers quite a bit of ground, but later in the race, during that last second, he's going much slower. And so I'd like my students to be able to describe this race in various words. And as I do that, what I would want is to avoid first words like speed and velocity. Two reasons for this. First, I want to focus this lesson on the idea of the rate of change and not make it a lesson on motion. I don't want to have confusion about the differing meanings of speed and velocity. The second, I want to be able to connect a graph to other concepts. So perhaps instead of a position time graph, this could be a graph of the number of people waiting on an escalator. Or it could perhaps be the number of pounds of bananas removed from a table at a particular time. So what I want you to do now is, with this graph, to consider a second runner in this race. This runner is going to tie the first runner. He's going to start and finish at the exact same time. The only difference is this second runner has a constant rate of change, meaning he covers the same amount of ground each second. So what would the graph for this runner look like? Well, if we turn on the slide, we can see that this graph is a line. And it's a line because it's a constant rate of change, okay? And this constant rate of change for the second runner happens to be the average rate of change for the first runner. Why do we use the word average? If we think about it in terms of grades, if I have an average grade of a 92, then my grade is the same as a student who are a 92 on every assignment. So an average rate of change is the same as that of a function with an equal net change, but at a constant rate. So let's watch this race. If I start the animation, we can see the blue runner starts out quickly and moves well ahead of the runner in red. But as the race goes on, the runner in red has a chance to catch up. And according to the graph, we can see that the second runner finishes at the same time as the first runner. Let's look at a second graph. Let's look at a second graph on a handheld version of the same document. What's different in this race than before? In this race, this runner is covering just a little bit of ground in the first second and carries very much ground in the second. This runner's rate of change is increasing. And so at this point, I'd like to plant a seed in my students' brains before we've ever really gotten to the calculus of the concavity of the graph. The rate of change of this runner is increasing, where the rate of change of the first runner is decreasing. And we can see the results when we play the animation and run that race against the same runner with the average rate of change. And so as this race takes place, what we want to look at is we want to decide, I want to ask my students, what's happening in this race as time goes by? originally, it looks like the runner in red is going to win the race easily. But there's some point in the race where the runner in red begins to not move as quickly as the runner in blue, and the runner in blue has a chance to catch up and win it. So let's take a look at one other runner, this time on the TI-84. We can see the graphs here. We have the runner in blue here, who has the average rate of change, a constant rate of change, that's the same as the average rate of change of the runner in red. But for a second, consider what would be different about the average rate, about the race run by the runner in red that we haven't seen yet. What unusual thing might happen in this race? Well, let's make use of the parametric mode in the TI-84. And what I'm going to do is I'm going to press second draw and choose clear draw so that I can watch the race run. And we can see the runner in red takes off really quickly and makes covers a lot of ground, creating great distance between him and the runner in blue. But at some point, the runner in red turns around. Maybe he dropped the baton. Maybe it's a relay race, but he drops the baton, he turns around, stops again, and then he has to go rather quickly in order to catch that runner in blue, and he's able to tie there at the end. This race had two places where there were turning points. There was the point where it looked like the runner in blue had no chance to win because the red runner took off so quickly. Then there would look like a point where, because the red runner had turned around, the runner in blue had no chance to lose. But in the end, he had to hold on for dear life and only hope that he could tie. One last runner that we could look at is perhaps a situation that students wouldn't see in a real world. Here's a position time graph of a runner in blue. And if this runner were to run the race against our runner with constant rate of change, he'd always be going slower than a runner in red. But at some point, perhaps he's Harry Potter and he apparates and he's able to move ahead, and though still moving more slowly, is able to tie the race. The key thing in all of these is that for all of these functions, they had the same average rate of change. The output of the position, the change in position was the same, the change in time was the same. And so we can see that if we look at the ratio of the change in position to change in time, it's 30 minus 0 over 6 minus 0. And for all of them, the average rate of change is 5. At this time, Jan's going to take it over, and she is going to talk about ways to help students calculate the average rate of change with their calculator, with their handheld.
Okay, thank you, Dennis. I'm going to share my screen here. So I want to first of all find some problems where students might encounter the average rate of change typically on the AP, typically on the AP exam. So I have a question that I have here, and let G be the differentiable function with the selected values given on this table. What is the average rate of change over G? And for some reason I started picking up my annotation. Here it is. So this, really no calculator is needed for this. We just need to make sure that we are emphasizing the difference quotient in the correct notation, where I have my G of 12 minus G of 0 all over the 12 minus 0. One of the first two difference quotients is what we really need to be seeing. Okay? Moving on to the next question. This average rate of change question was brought to us in 2014. The graph clippings are placed in the bin where they decompose from time t equals 0 to t equals 30. The amount of graph clippings remaining in the bin is modeled by this equation, 6.687 times 0.931 raised to the t power, where A of t is measured in pounds and t is measured in days. And students were to find the average rate of change over this interval and indicate units. Okay, I'm going to start with the Nspire. Okay, here we go. And when I start with the Nspire, what I always do is tell my students, I always have them open up a new problem for each, and for just a minute, for each free response question. And I always tell them, just go ahead and define the question, or define the equation for the question, and I just have them go ahead and graph it. And when they hit graph, sometimes they get worried about, you know, not being able to see the entire graph. And I always tell them, don't worry about that, because we don't need it for this particular problem. So I want to have the students find that average rate of change. So we're going to add a calculator page. And I'm not really sure why this annotation keeps coming up on my computer. So I would like to start with a fraction here. And remember that we had this stored in F1. So showing this notation correctly, I would have F1 of 30 minus our F1 of 0 all over our 30 minus 0. Okay, so when I hit enter, I get my average rate of change. All right, so there it is on the Nspire. Let's switch over to the 84. 84, it's very similar, where I have my equation, 6.687. I just type that into my y equals. And again, we're going to do that difference quotient. And this is in y1. Now, one thing that's really kind of slick to see here is the fraction is right here. Alpha x will pop up a fraction real quick. Okay, so then we are getting ready to do our function notation again. Alpha trace brings up my functions, and that was in y1. So I do y1 of 30 minus my y1 of 0 and then all over 30 minus 0. So again, I get that difference quotient, and just emphasizing the notation and having students be familiar with that. Okay, Dennis, I think you are up next. I am going to pass it to you, and he's going to continue with our average rate of change.
Thanks, Jen. Thanks, Jen. So what we'll look at now is this is at a different place than we were before. So students have started to learn calculus, and they understand derivatives, and they for me, this is where I've already finished covering the chain rule, and I'm starting into the idea of analysis of functions. So as you can see, we deal with two runners, A and B, competing in that same 30-meter race, both starting at time t equals 0 and finishing at t equals 6. The position of runner A is given by this function. This is that same concave down parabola we saw earlier. And so we're going to go to the next page, and we can see his graph. It's the same graph we saw before. And if we go on, it says runner B runs in such a way that her rate of change of position with respect to time is constant. And that we are asking, what would the position time graph for runner B look like? And we can go to the next page and see if we are correct. At this point, we're just asking students to kind of remember that idea of constant rate of change, and also to make connections with a previous experience in a previous exploration. And so we can see those two graphs are the same. And if I wanted to, I could go back and even watch this race. But what I want to do now is ask some questions of my students to get them into the context of the problem. So here we have a questions page, and it says, using f of x, write an expression for the average rate of change for runner A over the duration of the race from 0 to 6. And so a student can come into this box and enter an expression just like Jan did on the calculator page. So they could press Control Divide to get the horizontal fraction bar and do f of 6 minus f of 0, and then divide that by 6 minus 0. I want to reinforce at every opportunity this average rate of change notation, because on that AP exam, while there's only 1 point for finding that average rate of change for that answer point will not come unless I have this different quotient. And so now a student can press the menu button and check their answer and see that their current answer is correct. And they didn't have to enter it in this form. It would take equivalent responses. So if they decided to use a set of parentheses and division, they could do that. Now another question is, I want the students now to calculate the numerical value for that average rate of change of both runners. So they could go back and use the equation, they could go back and use the graph, but in the end I'm looking for a value of 5, and they could type in that value of 5 and check their answer, and they see that they're correct. And so in the next page, the expression for the function s of t, which I'm calling the position function for runner B. And the reason I'm using s is I'm going to start using that language of that secant line again. Runner B represents the secant line between time 0 and time 6. And so at this point, I'm going to pose a question to my students using f of t and s of t, write an expression for the function d of t, the difference in the position of the two runners as a function of time. Why do I want to know about the position of the two functions as a runner as a function of time? Well, if you go back and think about that race, we saw that the runner with the constant rate of change, was falling behind. The distance between him and the runner in blue was increasing, and it looked like he was going to lose until he started to close that distance. This race turned when the distance changed from increasing to decreasing, when that distance became a maximum. So if we look at this equation, what we're really asking is, when does the expression d of t equal f of t, d of t, which is equal to f of t minus s of t, when will that equal 0? When will that reach a maximum? So we're looking, when is the distance between these two runners a maximum? And depending on your textbook, you may have Fermat's theorem in there, or it might be just a simple numbered theorem. But Fermat's theorem says if f has a local maximum at or minimum at c, and if f prime of c exists, then f prime of c must be 0. So Fermat's theorem is telling us that the distance between these two runners is going to occur when the derivative of that distance between the two runners is 0. So we'll go back to our handheld document, and if we go to the next page, it tells us an explanation of what Fermat's theorem stated. And it says that on the next page, we can move the point on the x-axis, or the t-axis in this case, changing the value of c until the derivative is 0. And so we'll go to the next page, and we can grab this point right here, and we can move it, and we can see the value of c change, and we can see the value of the derivative change. And so the distance between them is increasing and has a positive rate of change up until time 3, and at time 3 that distance is now 0. Well, at this point, we'll go to the next page, and it says that on the next page after this, we'll notice that the line tangent to the position function of the runner A is parallel to the position function of runner B at time t equals c. What does this mean about the values of the slope of these two lines at c? What does it mean about the derivative of the position functions with respect to time at t equals c. So on the next page, we can see that at this value of 3, this tangent line is parallel to this secant line, that the instantaneous rate of change of the runner in blue is equal to the constant rate of change of the runner in red. And that's only happening at that point. That is the only point where they become parallel. So if we go to the next page, we just emphasize it once more in a little bit larger view. So why does that happen? Well, we're looking for where d of t, which is f of t minus s of t, is going to have a derivative equal to 0. And Fermat's theorem tells us that's happening, if the derivative exists, it's going to happen at some value c. Well, the derivative of d of t is just going to be f prime minus s prime. And so at some value of t, which is c, f prime of c minus s prime of c should equal 0. And solving for that, we see that f prime of c should equal s prime of c. So the derivative of the runner who's moving at a changing rate of change should be equal to the derivative of the runner at a constant rate of change. And so we go to the next page, and it says that we can see the graphs of the derivative of each position time function, and we want to know, does this graph confirm our answer? Well, hopefully our students will know that this s prime, without a label or without a color, would be the runner who's a constant rate of change. The derivative of a linear function is a constant. And the derivative of the runner in blue, well, his rate of change is decreasing. We saw from the race that he was getting slower. And it's only at c, when that distance between the two graphs is at a maximum, when the tangent line is parallel to the secant line, that the two derivatives will be equal. And so what we've come to is the consequence of the mean value theorem, that f prime of c for that runner will equal s prime of c. But don't forget that s prime of c is also the average rate of change for the first runner. So at some point when the slope of the tangent line is equal to the slope of the secant line, the runner's instantaneous rate of change is equal to his average rate of change over that interval. And that is the consequence of the mean value theorem, that f prime of c is equal to f of b minus f of a over b minus a. At this point, you'd want to be able to try to plant seeds into your student's mind about how will this consequence happen? What conditions have to be met? And we can look at other runners. We saw this race on the 84 earlier, and the same demonstrations we've been doing can be done on the 84 with the transform app. You can see here, this is the two runners we just had, and using the transformation app, I can move that tangent line until it becomes parallel. And I'll go ahead and type in 3 because we know that that's where it had happened. And by using graphical database files, GDB files, I can bring up each of those screens that we saw earlier on the Nspire. But on this graph, we can see that the distance between the runners is at a maximum at this point, and the tangent line is parallel, but it's also the distance between them is at a maximum here. These are the two places where we saw the race turn. The distance increased, then the runner turned around, the distance decreased and then increased again, and when it was at a maximum again, they were once again running at the same rate. So we can emphasize to the student, why does the distance matter? Another way to look at it is the distance increases as long as the velocity of the runner in blue is greater than the velocity of the runner in red. But at that point where the distance goes from its maximum, now the velocity of the runner in blue is smaller, and that distance will start to decrease. So in this case, the consequence of the mean value theorem is met twice. And we can see it here, same explanation again, that as we move that, the derivative is equal in 1, 2 places that they have the same rate of change. But what about Harry Potter? What about the one who apparated and cheated? What would that race look like? Well, if we look at it, we're still going to look for where the distance is at a maximum. But where the distance is at a maximum, we don't have a derivative. So Fermat's theorem doesn't apply here, so we're not getting the consequence that we were seeking. Or we could look at, and we can see in the graphical picture, that those two derivatives will never be equal. The runner in blue is always moving slower, except at the point where he's discontinuous. Or we could look at a graph with a corner. Well, here we can see that the distance is at a maximum, but the problem here is that, once again, the derivative doesn't exist. There is no tangent line there for it to have a zero slope. So if that derivative doesn't exist, then our condition isn't going to be met. And so at this time, Jan's going to take an opportunity to show you some ways to have your students explore intervals and to search for when this condition will be met so that they will get the consequence of the mean value theorem. So I'll give control to Jan.
Thanks, Dennis. And I will share my screen. Okay, so in this next section, we would like to work with a graphical exploration to help students with the conditions that must be met in order for the mean value theorem to guarantee that C value. Just keep in mind that there is a student exploration document that will be available to download with this activity. So before we get started, I would like to kind of go over the mean value theorem, which states if f is continuous on the closed interval a to b and differentiable on the open interval a to b, then there exists at least one C value in the interval AB such that the average rate of change is equal to that instantaneous rate of change. So we are going to start, first of all, with the Nspire. And if you look here, let's just kind of look at this document that we have here. I have the graph in blue, which is y is equal to x minus 1 to the 1/3 power. And then I have in red my secant line, and the intervals for that secant line that we're going to be working with are down here, kind of driven by the sliders A and B. And then this black line right here is going to be that tangent line that the k values up here are just basically the y-intercepts. And we know that that tangent line should be parallel to that secant line, so that is set up like that already. So the first thing I do is I look at this and I would ask my students, is this blue function, is it differentiable and continuous over its entire graph here that we see on the screen? And a lot of students have real trouble right here with deciding, is it differentiable at x equal to 1? So in the very beginning, I always like to have my students explore things graphically. So I always tell them, well, let's just look at the graph. So let's kind of go up here. My function, I do believe here, is y1. So I'm going to find the derivative. A couple of ways you can get the derivative. I'm going to do shift minus. That's our template, real quick template for the derivative. And then I have here my f1. I do believe my function was in f1. We'll find out if it was not. And I hit enter for the graph. And yeah, it was. So we can look here at the graph of the derivative, and students immediately see that we have a vertical asymptote here. So then they're like, okay, so we have a point that's not differentiable on our original function x minus 1 to the 1/3 power. I'm not really sure why this annotation request keeps coming up, but I will decline it. Okay, so then another question I would ask my students is to say, give me 3 intervals at which the mean value theorem conditions are held.
Jan, can I just
Yes.
help you real quick? Just slide that annotation request off to the side and the next time it shows up, and we can think about it.
Thank you very much.
Yeah.
That's why I have a partner. Thank you, Dennis.
Yeah.
Okay, so I am looking at the interval from -1 to 3, and I would ask my students, are the conditions met in order to be able to use the mean value theorem? And no, they are not, because I've got that value of x equal to 1 there. So I would ask them to just kind of play around with these intervals and say, okay, is there a value, or give me 3 different intervals at which that conditions for the mean value theorem would be met. And then this tangent line right here would be to say, okay, I've got an interval set up from 1 to 3 here. From 1 to 3, it looks like, yes, the interval is continuous and differentiable. So I can look at, and notice it's differentiable on the open interval, and that is fine. I can explore this tangent line to see, would there possibly be a tangent line that would be parallel to the secant line? And yes, there is. We might have to play around with the step a little bit on this slider, but we can pretty much kind of guess that it's somewhere about 1.5. And again, we could look at different intervals and have students kind of come up with some values of C that might be true. So again, when starting with the mean value theorem, I always like to get the students to kind of graphically give me that C value. How could we figure that out? Well, remember, it's when the average rate of change is equal to the instantaneous rate of change. So I've got, it's like when my derivative is equal to my average rate of change. So I've already got my derivative here. So I would ask my students to, let's put in our difference quotient. So I'm going to get my fraction here, my function notation. And remember, this was F1. So I have F1 of, oops, let me type everything in. F1 of 3. I usually go from 1 to 3. So I'm going to use that here because that's what I had found earlier. And then 3 minus 1. Okay. So I have my average rate of change and my derivative both intersecting in 2 places. So this is another good point to bring up. There might be 2 points of possible values of C, but which one do we want? Well, we only want the one that's in the interval from 1 to 3. So that's the point I'm going to find. And we do that by hitting Menu, Analyze Graph, and we want intersection. So we're going to go lower bound, upper bound, and there's that point of intersection. I'm going to move it up here so I can see it a little bit better. Now, we all know in calculus that we want 3 places past the decimal. And a lot of times I have students that they just get kind of hung up on not knowing how to change that point of intersection that's only showing 2 places past the decimal. So I always tell my students, just hover over the X value, do not click, and then come over and hit the plus button, and that will increase the number of digits that you are seeing. So then that way they are able to place all 3 of the digits that they need. Alrighty. One other thing I want to kind of look at is going back to this graph and going back also to the impacts at which Dennis had up earlier. One of the bullet points is asking if the converse of theorems are also true. So I would ask my students, is the converse of the mean value theorem also true? So let's kind of explore what that would be. Is if there's a slope of a tangent line that is equal to the slope of a secant line, then the function will be both continuous and differentiable on that interval. And students can kind of investigate that. So I'm going to come down here where I get -1. So I'm looking from -1 to 3. And let's take that tangent line down here. And it looks like I have a tangent line and a secant line being parallel there. But the question is, just because I have a secant line and a tangent line that are parallel and the C value looks like it's occurring, are the conditions for the mean value theorem being met on that same interval? And the answer is no. So that is a false statement. The converse of the mean value theorem does not hold. Okay, or is not true. So I am done with the Nspire. Let's switch over to the 84. If I go to the graph, make sure I have the correct file up. I do. This is the same graph. I'd like to do something different first before I do the same thing that I just demonstrated on the Nspire. I want to use Dennis's idea that he mentioned earlier, where you look at the distance between the graph and the secant line. Can you estimate, or I would ask students, can you estimate where that greatest distance would be occurring? Obviously, it's not up here. And again, I'm looking from 1 to 3. And so as a student, I'd probably look at that and say, oh, it probably happens about 1.5. So let's draw in a tangent line. So I'm going to hit second, draw, which is program. And notice number 5 is tangent. Now, notice that the cursor is on my secant line. That's not what I want to draw a tangent on. I want to draw a tangent line on this blue function. So I'm just going to type in, we said as a student they would probably 1.5. And then the tangent line is drawn in, and I'm going to look at those and eyeball it right here. Does this blue line, this blue tangent line, and the secant line look parallel? No, so I really don't quite have it. So I would hit second program, which is draw. I'm going to clear that draw out. And I'm going to try something else. So I'm going to try and do a tangent line again, but instead of 1.5, let's put 1.3. So be sure you change. Oh, now I've gone too far the other way. So again, this is kind of like trial and error, getting kids to discover how can I get that secant line and that tangent line parallel? What C value would that be? So I'm going to clear that draw one more time and go ahead and put in that tangent line. And that would be at, let's put 1.38. I think that was pretty close to the answer if I remember rightly. And there it's looking much more much more parallel there. Okay. Alrighty. So let's go back then. That's one method that you can use your tangent line on the 84 for here. Alrighty, so I'm going to bring up my tangent line. It's down here. I have it pretty low. Now notice these A's and B's are a little bit driven, a little bit different than on the Nspire. And my my emulator runs a little slow because of the type of the equations we have written in here. So I'm going to go 1 to 3. I'm going to leave that the same. And notice I just arrow up and down to toggle to the different variables. And I'm going to get this tangent line back up here where I can see it. Oops, I went the wrong way. So as you can see, my emulator is running a little slow. On the handheld, it does not run this slow. It runs much quicker. And remember, these GDB files will be available for you to download. So again, the students can estimate where they think, or if one would occur between 1 and 3. Is there a tangent line that is parallel to the secant line? Can we estimate or can we evaluate that C? And yes, we can. Okay. So on the 84, how do we do that? We want to get that specific value. We've discovered that yes, there's a possibility. So I'm going to go to my y equals first of all, and I need to shut off. Oh, and by the way, transformation app is what this is being ran under. So make sure that you turn on your transformation app. If you just hit app and then you arrow up, it's usually the last one. If you hit enter, that's where you turn it on and turn it off. Okay. A lot of times I'll have students come to me in class and they have that little symbol right there on the left of the Y1 and Y2, and they're always wondering what those are, and I always show them how they can shut those off. So we're going to shut the equation off right now. Because I want to graph the derivative. Okay. Again, just like before, the students are wondering where is it differentiable. Maybe they're not for sure about that vertical tangent. And how we can do this on the 84, we can hit alpha window. See the derived number 3 brings us our template for x. Notice up here y3 is where my function is at, so I'm going to hit alpha trace y3. So this means I'm going to find the derivative of y3, and I want to graph it for all values of x. So that is how, without a cast, how you can graph your derivative. Let's look at that. Yep, that's the same graph we had on the Nspire. So let's go back, and now I want to go down here and graph the difference quotient so I can observe where the average rate of change is equal to the instantaneous rate of change. Now, another way you can find your division, your fraction key, is hit alpha y equal, and that's number 1. But again, I truly do like that alpha x to get the fraction key right away. And we're going to do our y3, so it's alpha trace. And I think I was doing between 3 and 1 again. I think that's what I had it set as. And that is alpha trace y3. So I'm going from 3 to 1, making sure that I have all the notation there correct. If we get an error message, no big deal, we just fix it. Then I hit my graph. There we go. And again, the opportunity to talk to students about, even though there may be more than one point at which the average rate of change intersects with the instantaneous rate of change, we are only looking for the value between 1 and 3. So the way we find that point of intersection on the 84 is to hit second trace. I hit alpha. And then I hit number 5, intersect. Is this the first curve? Yes. I hit enter. Second curve? Yes. I hit enter. But I need to make sure that my cursor is over closer to the one I want to actually find the point of intersection of. And I hit enter. And if I look down here, the lower part of the screen, I have my point of intersection of 1.384, which was what we had before. Okay, so the next thing I want to do is I want to go back to my Nspire. And that was a pretty simple function there, just x minus 1 raised to the 1/3, not a lot going on with it. So I want to go to maybe a graph that has a little bit more on it. And if I look here, I have a lot more points of, well, I actually have a discontinuity here, removable, a non-removable discontinuity, and I have some other non-differentiable points. So what I like to look at is maybe the point from where the secant line goes from -1 to 1. Now, I know my students would put a point here and try and graph the secant line with the value for 1 being up here at about 1.5. This is a very good example of kind of driving home the point that the function needs to continue on the closed interval. And if you look here, 1 is defined down here at -1/2, not up here. So this is a good graphical to get students to kind of look at that. And again, there's a lot going on with this page. So I would probably add, let's add a graphs page, number 2. And I'm going to graph that derivative. Now, that derivative, whoops, let's arrow up. That function was in, let's just call it f of x. Okay, so I'm going to do the derivative. So another way of getting the derivative is to hit this template key right here, and you'll find the derivative right here. And then I have f of x. I do believe it was defined as f of x. Or we can hit F1. Whoops, look what I'm doing. And let's see if we get our derivative. So there's our derivative. What the students can have a very good visual of where where that function is defined and where it's differentiable and where it's not. Where we have this sharp turn right here at -2, it is not differentiable. Right here at 1, which we knew that it would not be differentiable because it was a discontinuity, and again over here at 2, where I have a vertical asymptote. All right, and again, I could ask my students a lot of questions. Give me the intervals at which the conditions for the mean value theorem would hold. Give me one interval where the conditions for the mean value theorem do not hold. So we can go into a lot of questions asking for that. Switching over to the 84. Okay, now this is a good learning point of I had all this from before, and I need to bring up a new list of equations. So this is saved under a GDB. So I'm going to go to second draw. I go over to store. This is stored in my calculator under GBD 9. So I'm going to recall GDB. This is number 9. Hit enter. Now when I go to my y equals, I've got my new equations. Now, we have to talk a little bit about the 84 with this complicated function, this piecewise. It has a lot of parts to it. Right here at this point, at 1, this is supposed to be an open dot. And down here at 1, -1/2, that is my closed dot, like what we have on the Nspire. And this little connection right here is not supposed to be there. But because of transformation app and everything else going on with it, we kind of have those extra things there. But again, everything's driven down here. The graph is the blue line. The secant line is red, driven by the 1 and 3. And we can change, or by the A and the B. And we can change to the, this is a lot slower because it's a more complicated function. Oops, and it all just went off. Okay, but again, it's workable on the 84, but again, moves a lot faster on the handheld. Don't worry about that. That will work better for you on that handheld. So a reminder that there's a student activity sheets that will go with these activities that you can download, as well as all the files. Alrighty, Mike, are you ready there to take it back?
Thanks, Jan. I am. Thank you. So as we begin wrapping things up tonight, if you have any last-minute questions for Dennis or Jan, please try to get those asked. I know they'll do their best to get those questions answered. One thing I'd like to share from our website, education.ti.com. Actually, a couple things. Probably the biggest thing, in case you're not aware of it yet, under the Resources tab, there's something titled TI in Focus. If you click on that, this is a wealth of resources that's going to be continuing to build as each year's AP exam rolls on. So let's say you're looking to teach a certain topic. For instance, let's say you're going to pick the fundamental theory of calculus. Again, we have information and data that started being gathered in 2017. So we have 2017, 2018's information. And so if you click on, for instance, 2017, there's some really great resources here, like videos that you can watch, specific technology files for both the 84 and for the TI-Nspire. I personally used the PDF slides with my students, helping them try to understand some of these concepts a little better. I just really appreciate the way that they were presented. It was a lot of times in ways that I hadn't thought about presenting that way to my students in the past. So if you haven't seen these yet, please check them out. I think they're definitely worth a look, and I've used them again with my students and had some really great success. We're excited to have the T-Cubed International Conference coming to Baltimore in early March this year. It really is a great place to connect with like-minded educators where you can not only learn about brushing up on your content or learning new content, but also connecting content and pedagogy. And then after the conference, you have these lifelong friends, which has been one of the biggest benefits for my life. So please visit our website to learn a little more. We do have some special pricing for the conference that's going to be ending at the end of October. So please feel free to, again, visit our website to learn a little more. And then Dennis.
Thanks. Just to put in a plug, if there's any participants here tonight from Georgia, the Georgia Math Conference is this Thursday and Friday, October 18th and 19th. And on Friday morning, Vicki Carter, who you know if you're a regular attender on these webinars, a T-Cube National Instructor, will be presenting all morning on calculus. So this is a great opportunity if you're a Georgia instructor to come learn calculus from someone who knows it very well.
Thanks, Dennis.
Thanks, Mike.
I also want to mention that we have a new contest that's currently going on. This contest allows you to win prizes that hopefully will motivate you in your classroom. So to win these prizes, you just need entries, and you can visit TI-Nspire.com to learn all the different ways that you could possibly gain additional entries. One of which is by what you're doing tonight, just attending a webinar. So if you go to TI-Nspire.com, there'll be a place for you to enter a code for attending a webinar. And tonight's code is not case sensitive, and the code is reason with MVT. So REASONWITH MVT. When you leave the webinar tonight, a brief survey automatically will appear in your browser. Your feedback guides us as we plan future online events, and we really hope that you'll share your thoughts. Feel free to continue the conversation tonight on any of the major social media outlets. To receive a certificate of attendance, go and click the link in the chat window. Also listed is a link for the documents that were used tonight by Jan and Dennis. And if for some reason these links aren't working for you, don't worry, you'll automatically get a follow-up email within a couple days. And that follow-up email will be containing the links for the certificate as well as links for the documents and the recording of tonight's webinar. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. Last but not least, if you're in need of any post-webinar follow-up, feel free to give us a call at 1-800-TI-CARES or drop us an email at ti-cares@ti.com. We'd love to hear from you. So thanks so much, Jan and Dennis, for everything you shared tonight. We really, truly appreciate it.
Thanks, Mike.
Yeah, thanks, Mike.
And thanks, everyone, for joining us. We hope to see you back online real soon. Have a great night.